So we have the problem statement for the dependent two sample t-test over here. The objective of performing this test is for Anita to prove that the competitors of her employer are in fact pricing their products competitively. When I say competitively, they are pricing their products at a lower price than what her employer is offering. The data for this is stored in two vectors. The vector A shows the competitors' prices, vector B shows the employer of Anita, their prices for same products. So these two values are matched. 55 and 65 belong to the prices of the same product on the two different portals. Likewise, 35 and 45 is matched, 19 and 14 is matched, and so on. The total number of elements in both of these vectors is nothing but 11. Totally, there are 11 prices for both of these vectors. The first step in performing the t-test is to compute the differences of these two vectors for all the items matched one on one for both of these vectors. So doing b minus a, I am storing it as d. So these are the difference vectors. Now the null hypothesis for this t-test is mean of the differences equals 0. The alternate hypothesis is nothing but the opposite of this. This is the alternate hypothesis. Now we want to use the t-test to actually test if the null hypothesis is in fact valid or not. So the first step to do that is to compute the t-statistic. To compute it, first step you need to compute the sample mean. In this case, the mean of the differences. So that turns out to be 12.54545. Now we want to compute the standard error. The first step in computing the standard error is to compute the standard deviation itself. So this is the standard deviation. You can compute standard deviation using SD function. Divide that standard deviation by the square root of total number of observations. You will get the standard error. So 5.510921. This is the standard error. To compute the t-statistic, all you need to do is to divide mu by the standard error. So mu by SE, and t-statistic is 2.276472. Now we want to compute the p-value. Now this is the formula I have used to compute the p-value. Let me explain this, what this actually means. We saw that t-statistic value is 2.27. Where this falls on the t-distribution curve. So suppose this is the t-distribution curve. It's not shaped well, but that's okay. The center of this t-distribution curve value is 0. Suppose the 2.27 falls over here. The p-value is nothing but the region to the extremes of this value, the absolute p-value, the extremes of the absolute p-value. The absolute t-value includes the negative side of the t-distribution curve as well. So this shaded region I have over here is the area under the curve that we want to compute. Now, in R programming language, the pt function, you pass a t value to it. You also pass the number of degrees of freedom as 10 in this case. If you compute this, what this will return is, suppose in this case, our t equals to 2.27. What this will return is the area to the left of this point. The left of this point, the entire area over here, all the area over here, that will be returned. But what we need is the area to the right hand side of this area and this area. Let me draw it in another color. We need this area. To compute that, we need to maneuver it smartly. How do we do that? So what I am doing is I take the negative value of t. So pt of minus t and 10 is going to give me this area on the left. Multiplying it by 2 is going to cover both the shaded regions on the left as well as the right. Now this becomes the p-value, and that is exactly what I have computed over here. 2 times pt of minus 1 into t statistic. The number of degrees of freedom is 11 minus 1 equals to 10. If you run this, we get the p-value as 0.04606. Now, since the p-value is lesser than alpha of 0.05, we reject the null hypothesis. What is the null hypothesis? The null hypothesis is the difference of the means equals to 0. So we reject that claim. We don't have enough evidence to conclude that the difference is in fact is 0. So it's fine. So we have a statistical basis to prove that the prices of the products in these two different portals are in fact very, very different. All right. So we have p-value as this. Let me write it down. And t statistic as 2.2764. Now let's actually use the t-test function to compute all of this. We manually did the computations. Now let's use the t-test function now. T.test is a function that is provided by the base R programming language itself. You don't have to install any package or such. It is available by default. On running this, notice I have set mu equals to 0 because in T statistic formula, our assumed value of mu, the T statistic formula is x bar minus mu by standard error. We have computed only the x bar because mu is 0. That's why we did not specifically compute it. And while calling the t-test, you have to explicitly set mu equals to 0, or since this is a dependent two sample t-test or a paired two sample t-test, you can pass in the two vectors that you are comparing and set paired equals to true. Both of these functions are equivalent. The output is exactly the same. If you notice, the output of the first function and the second way of operating, both of these are exactly the same. Well, you may notice that the 95% confidence interval is different because I am passing different inputs, and because of that the confidence intervals are different here, and that is not relevant at all in this case. What is relevant is the t statistic, which is computed over here, and the p-value, both of them match. The t statistic comes out as positive in the first case because it is referring to the right hand side tail of the t statistic, whereas in paired t-test, using the paired equal to true argument, it is coming as the left hand side tail. So that is fine. So that serves all the purposes for computations. That's perfectly fine. And the values that we computed, the values of both t statistic as well as the p value that we computed match exactly. So p value is 0.04606 and t statistic is 2.2765. So that's how you perform a t-test in the R programming language.